Welcome. In this video I'm going to show you how you can perform a modified log likelihood goodness of fit test using Python and not my own library. So I'm using Python version 3.818, and in this video I'll actually focus on how to perform the test and get the output, not so much if you should be using this test. To show you how this can be done, I'll be needing an example data, so I'll load in pandas. And then I have a file called GSS, General Social Survey 2012, adjusted for example purposes, and I'll store that under a data frame. So just loading in that file. I actually don't need all the data in there. I only need one nominal field, so I'm going to be using MAR1, that's the marital status. So I'm going to select that, and just to get a quick impression, I'll use value counts so I can see which option was chosen how many times. So for example, 181 people selected widowed. I have a separate video where I show you how this can be done simply with one function in my own library. But if you don't want to use my library, there are other libraries that can actually do this. SciPy has an option. So we can use power divergence, because this test is one option with power divergence test. We give it actually the counts that we set earlier, and then as lambda we simply say that we want the mod log likelihood. We then get both the test statistic, which is a chi-square value, and the p-value, so the significance. Stats models will actually do the same, so it has power discrepancy, and because of that we can also use that. It needs the frequencies, but it also needs expected counts. So the expected counts, I'm simply going to say, well, it's going to be the each category equally distributed. So take the sum of all the frequencies and divide it by the number of frequencies. I'll store that as one list with the number of categories, so my length of my frequencies. So that should give me the same value, and there were 5 categories, so 1, 2, 3, 4, 5 times 388.2. This should give me the same result, and if we wait a little bit, I didn't activate the power discrepancy function, so that's why it wasn't happy, but now it gives me the same result. Again, the test statistic and the p-value. Now, if this p-value is below 0.05, which is the usual threshold, we would say there's a significant result, and therefore that in the population not all categories will be equally distributed. The E minus 273 makes this below 0.05, because it means we have to divide all of this by 10 to the power of 273. If you want, you can also do all of this without any libraries. So we first then convert the data back to a list, so that's a Python's native type. We then remove any missing values, so we loop over the entire data set and remove anything that is none. And we need to get all the unique categories, so I can just translate the data to a set, and that should give me the 5 different categories. How often was each actually done? So I can't use that values count because that's a pandas function, so I simply go over and count and get the same result. Also useful is the number of categories, which is simply the number of frequencies we have, and the total sample size, which is the sum of those frequencies. As expected count, I'll be using again the same trick as earlier. I divide the sample size by the number of categories, and that gives me the expected counts. Alright, then I finally need to fill out this complicated looking formula. I will be using Python's native library for the logarithm, which is the natural logarithm, and then I can actually fill the whole thing out in one go. It's 2 times, so that's the 2 times over here. Then the sum, so it's the entire sum of the expected count, so I have those under EI, and then times the logarithm, the natural logarithm of those expected counts divided by the frequencies. And I do that for all my categories. And that gives us that same test statistic, the chi-square value. The degrees of freedom is simply the number of categories minus 1, so that's fairly straightforward. And then we need the chi-square distribution. Now this is available under SciPy stat, so I will be needing that one. If you are interested, I have a separate documentation on how you could even do the whole chi-square distribution without any libraries, but That's a bit usually a bit difficult, so most often people will just use the site-by-stats library. I'll do the same. I'll use the survival function, and that should give me that same p-value as we saw earlier. If you want, you can do corrections. So there are actually a few. Pearson and Williams, for example, they adjust the chi-square value. So for Pearson, it's straightforward. It's the sample size minus 1 over the sample size. And for and when you multiply the original value with that. Well, for Williams, we have this complicated looking, but we have all of this case, the number of categories, the degrees of freedom we have, so we can just fill that formula out. But this one, you say, well, we take the original and we divide by this factor. So that gives us two slightly different chi-square values. Yates is again slightly different. It actually adjusts the original observed counts. We subtract a half or we add a half depending on if it was greater or less than the expected count. So we can do that in a loop and then simply adjust them accordingly. Alright, and that was it. I hope this video was helpful and thank you for watching.